If you take a look, 12.1b, we're going to be doing the ellipses. Now, ellipses and circles equations, you kind of can think of a circle as a perfect ellipse. So an ellipse is just something that kind of looks like an egg. So it might be elongated one way or the other. So that's what we're going to talk about today. So there's lots of pieces and parts to an ellipse. We have something called the foci or focus. We have a major axis, which could be going this way if the egg is laying on its side, or we have a minor axis, which could be going that way. We do have a center just like a circle, but it is where the minor and the major axes cross each other. We are not going to really look at where the foci, there's formulas for that, but for timing purposes, we're really going to talk about the minor axis, major axis, and the four vertices. You call the ones along the major the vertexes. You call the ones along the minor the co-vertices. So it depends upon which way it's laying. But as we go, you'll see how those work. Now, these are all a part of something called a conic section. If you set two cones upon it themselves, so their points are touching and they are perfectly lined up. If you cut it through and you have it slightly at a slant and it only hits one of the cones, you get an ellipse. If you would be perfectly parallel to the base, you'd get a circle. If you cut it through with a plane, and you'll see you get two things that look kind of like parabolas. That's what a hyperbola is. And then here's your parabola. So those are all called conic sections for that reason. They all can be derived from that arrangement of two cones. So what is the equation for the ellipse at center 0, 0? So basically, I think the only thing you need to copy are those things right there. Okay. So you might notice they look a lot like a circle. They look a lot like a circle. So x squared over a squared plus y squared over b squared equals 1. So you'll notice they're both squared. They're both positive, except now we have some fractions across. If the larger number is under the x, so here we're assuming that a is the larger number. If the larger number is under the x-axis is our major axis, so it will be an egg shape laying on its side. If the larger number is under the y, then it is going to look like an egg that is standing up on its tip. So that's the main difference between these two. A circle is just an ellipse where the a and the b match. It's the only difference. So for a circle, you might have a squared over 4 plus y, or x squared over 4 plus y squared over 4 equals 1. So if the a and the b match, it's a circle. If the a and b are different, it's an ellipse. But they're both squared, they're both positive, and that's the way you can kind of identify what is an ellipse. And don't worry about this too much. That will be helpful when you go to make the co-vertices and the vertices, which we'll talk about when we do an example. But I just want you to get in the habit of recognizing what do the equations look like. So technically, they're just a lopsided circle. Circles are a type of an ellipse. Remember back in geometry, quadrilaterals, a square was a type of quadrilateral, but it was the most perfect one. Well, we can kind of think of a circle like that. A circle is the most perfect type of ellipse. Now, if you change the center of your in an ellipse or a circle to HK, do you see how you have the H and the K by the X and the Y? So it looks very similar to what you've seen in the past. Let me make that as big as here. There you go. So again, if the larger value A is under the X, it's going in the X direction for our major axes. But now just the center is at HK. Same thing here. Our center is at HK. The larger number is under our Y. So the ellipse is standing up and the major axis is going up and down. And again, don't worry too much about that. When we go through an example, we'll break that down and you'll be able to kind of hopefully understand what all that stuff down there means. So if the larger number is under the x, it's going to go in the x direction. If the larger number is under the y, it's going to go in the y direction. To get an ellipse, you have to have the x squared and the y plus the y squared equals a number. If you have a minus in between them, you get a totally different shape. So it's kind of interesting. All you got to do is change that plus symbol in the middle to a minus. You get a totally different shape. So let's look at an example. That's the best way for me to kind of describe what happens. So we have this equation, x squared over 9 plus y squared over 25 is equal to 1. Now I'm going to do a little rewrite here, okay? I'm going to rewrite as x squared over 3 squared plus y squared over 5 squared equals 1. Now, you might notice that the larger number is under the y, so our major axis, or in the y direction, we are going to have the egg standing up, elongated on the y direction. Okay, so what do we know? Well, because it's an x squared, and there's nothing added on, the HK, or our center, is at 0, 0. So that's the first thing you find, just like you find a circle. If that was a circle, same thing would happen. Our A value is 5. It's under the y. So that's going to take us 5 units away in the y direction. So what you're going to do is we're going to add 5 and subtract 5 from our y. So we're going to, so that would be our vertices. So there's going to be 1 if you add 5 to the y direction, the y value, and if you subtract 1 on the y direction, or from the y value center. Now our b value is the smaller one, that's 3. It's under the x. So that's called a covertice. There's 2 of those. We're going to add 3 to the original x value. We're going to subtract 3 from the original x value. So that would be 3, 0 and negative 3, 0. So we're always adding or subtracting those from our center. And so let's go ahead and draw this, and we will label things as we go. Okay. So at 0, 0, put a little thing that's marked in the center, just like we did for our circle. But remember, our circle, if we knew the radius, we counted that many left, that many right, that many up, that many down. Well, now we have to be a little more careful. This is going to be how many we go in the y direction, because that number was underneath our y. So from that center value, count up 5 and count down 5. That should line up with those points right there. Label those as vertices. Now this was under our x. So from the center, in the x direction, we're going to go 3 to the left and 3 to the right. For the circle, we went the same amount up and down and left and right. Here we go different values up and down and different values left and right. And then those are marked as covertices. And then we got it, and then you make an egg. I don't know if they do. No, they don't. So just make your egg shape as best you can. Okay. Now up at the top, let's look at the instructions. It says graph it, identify and label the center, the vertices, and the covertices. We are not going to worry about the foci. We just don't have time, so scratch that part out. And if that part is mentioned anywhere, we're just going to skip it. So that is how you graph an ellipse that's at the center 0, 0. Pretty straightforward. If it's under the x, that's how many, take the square root, that's how many you go in the x direction. If it's under the y, take the square root, that's how many you go in the y direction. The thing to remember, they always have to be squared, they have to be added, and they have to equal 1 for this to work. They can't equal another number. If they equaled 7 or something stupid, we would have to deal with that. Any questions before I move on to the next example? Okay, let's do another one. So now I mentioned that our equation had to equal 1. You'll notice all those equations you wrote down earlier were equal to 1. This looks very much like you might see for a circle equation, right? X squared plus y squared equals a number. But you'll notice how they have different coefficients. That different coefficient means that it's an ellipse. It's been elongated in one direction a little bit. Now, to get it equal to 1, you just have to look at the right number, whatever that number is, in this case 100. We're going to divide both sides by 100. Now, when we divide by 100, we have to do it for all terms. Okay? And now we're just going to make it look a little nicer. You should be able to take the number 4 into each thing, but the key is it has to equal 1. Okay? 4 does go into 100 25 times. 25 does go into 100 4 times. It's got to equal 1 for this formula to work. Okay, so now we have it in our standard form, and so now we can find what we need. I'm going to rewrite this one as 5 squared and this one as 2 squared, just so I have those numbers kind of popping out at me. Okay, now our center is still at 0, 0 because it's a plane x squared, nothing added or subtracted. It's a plane y squared, nothing added or subtracted. Now let's talk about the vertices. The vertices come from the fact that the larger number is under our x. So our a value this time is plus or minus 5. So in the x direction, we are going to add or subtract 5 to our original HK, our original 0, 0. So that's going to be 5, 0 and negative 5, 0. Okay, so this time our vertices, our major axis is going in the x direction because the larger number was under our x. The co-vertices are from the number that is under our y. That's our b value, which is plus or minus 2. And that's going in the y direction. So if it's going in the y direction from our original center 0, 0, the y's we're going to add 2 and subtract 2 from the y value. So that's going to be at 2 and negative 2. So you notice I added and subtracted 2 from the original y value. So now we're ready to graph everything. Okay. So go to your center first, just like when we did circles. Put a dot at our center, label it C. Now under the x was a 5 squared. So in the x direction, we're going to count 5 to the left and 5 to the right. And that should coincide with our vertices. And that's the point, 5, 0 and negative 5, 0. Perfect, okay? And then we're going to label those with a V. The reason we label those with a V, that's our bigger number. Now the co-vertices are in the y direction, we're going to go 2. So we're going to go up 2 and down 2. And we're going to label those as co-vertices. And now that we have those, that should coincide with that. And now we're going to make our elongated egg shape. Okay. And that is how we do one that is not in standard form. Yes. Okay. Everybody good with example 4? Okay, no problem. Yes. Okay, so if you'll notice that our x is squared and our y is squared, they're both positive, And if the coefficients were the same, we would know it's a circle. So if they both said 4x squared and 4y squared, that would be a circle. But if they're both, if they're different, then we have to get it equal to 1 because that tells us it's an ellipse. And standard form is always x squared over a number plus y squared over a number equals 1. So it's just a matter of recognizing. If it's x squared plus y squared equals a number, circle. X squared plus y squared equals a number, but they're different coefficients, that's an ellipse. And you just have to divide so that it's equal to 1. So I divided by 100 so that both sides, or so that number is equal to 1. That's the major concern. Can I get that number to equal 1? Any other questions there? Yes. Yeah, well, come here.
So, you know, like for verbs, there's 5 and 0 and negative 5 and 0. Like, can't we just make like
plus or minus? Yes, that's a very good point. So I like that. So one of the things you can note, and let me put it down here, you could write the vertices as plus or minus 5 comma 0. If you want to write that as a shortcut, that plus or minus notation. So that's a very good point. We could also write that one like that. You can write that in that slightly different form if you want. That works perfectly for me. So if you like to write that plus or minus, and that's because when we take the square root of that, we get that plus or minus. So feel free to rewrite the vertices or covertices with that plus or minus notation. That does work for me. Any other questions about example 4? Yeah. Yes. Oh, isn't it kind of interesting? It does. It flip-flops because here, since we divided by 100, the 4 went into the 100 25 times, and the 25 went into 100 4 times. And so it does end up flip-flopping, especially if these two multiply to give you your back number. They're always going to kind of do a swap. If that's the case, they don't always equal that number when multiplied, but that's very common. That's a very common thing. Yep. It's just kind of cross cancel or cancel, just division does that weird stuff to it. Okay, now here is one. It's already equal to 1, so we don't have to worry about putting it in a standard form. Let me write it a little bit larger over here to the side so we can kind of see it a little bit more. So how do I know when it's an ellipse? Well, I have the x squared plus the y squared equals 1. That's indicating that it's an ellipse in standard form. Now, to make it a little nicer so we kind of see those a and b pop out at us, let's rewrite that as x plus 2 squared equals, or x plus 2 squared over 2 squared, and y minus 5 squared over 3 squared equals 1. Now, the larger number, the original 9 or 3 squared, is under the y, so our egg is going to be going up and down. Okay, so we know our egg is going to be going, or an ellipse is going up and down. So we know that the center is our HK, and just like when we did circles and many other things we've done, we're going to use the opposite of what we see here because x plus 2 equals 0 at negative 2. So it always does that flipping to the opposite. Hopefully you're getting used to that pattern happening. So that's negative 2, 5 is our center. Now let's start with our a value. Our a value is plus or minus 3. That's always the larger one. That's under the y. So we're going to add or subtract 3 to our y value, and that's going to be our vertices. Our first vertex, if we add 3 to the y value, is negative 2, 8. What's our second one? Well, we have to subtract 3 from our y value. So that's negative 2, 2. Okay, so I added 3 to my 5. That's where I got the 8. And I subtracted 3 from my y value of 5. And that's where I got the 2. Okay. Now, the b value is underneath my x. That's 2. Since it's under my x, these are co-vertices, they're smaller. We're going to add or subtract 2 from our x value. Now, our original x value was -2. If I add 2, I'm going to get 0. The y value doesn't change. And if I subtract 2 from -2, I get -4. Now, if that confuses you, we can go to our picture. We can label the point -2, 5 as our center. We can count 3 up and 3 down in the y direction. And you should get those points. If you don't get -2, 8 and -2, 2, then you calculated those wrong. Those are labeled as vertices. Now we need to go 2 in the x direction from center, 2 to the left of center, 2 to the right of center. Those are co-vertices. And those labels should match those 2. If they don't, you did something wrong. And then make your egg shape. And I'm very, very good at making ellipses, as you can tell. So those are ellipses. So that one had the center at a different point. Again, we're not finding the foci, so if you want to cross that out. Yes? So to find the vertices, because there's a 3 under the y value, I added and subtracted 3 from my y value. Because there was a 2 squared under my x value, I added and subtracted 2 from my original x value. So if it's under the x, we add or subtract it from the x. If it's under the y, we add or subtract it from the y. And you're always, the original number's square root is what you add or subtract. Okay, the square root of the original number. Any other questions about example 5? Okay. And then we have some equations here. All of them are already in standard form, so they're ready to go. So if you could identify the center, instead of identifying the length of each axis, just tell me the A, the B, and the vertices and the co-vertices. Okay, so exactly like I had done in the examples. And you can label them on there. You can show me the math like I had done. So I need the center, the A, the B, the vertices, and the co-vertices, and then you're going to graph each of those. So if you could please use the time you have right now to work on the problems you see there. And then next up, we're going to do hyperbolas. That's going to come next. So there you go.